In this section, I'll introduce some fragments of a SysML v2 model and then kind of bring it all together in a simple example. And just to give you some highlights of what SysML v2 looks like. Let's start with this part definition, or part def for short, for a vehicle. So the part def is analogous to a SysML v1 block. And you see it has 4 compartments that characterize this vehicle. It includes attributes, ports, actions, and states. It can include other compartments as well that provide other features of the vehicle. Let's take a look at the attributes for starters. You see the mass, and you see a little symbol there with the colon greater than sign. This is saying that this mass is a kind of mass from this library called the International System of Quantities. This is a standard library within SysML v2, and it contains all of the different ISO quantities, International Standard Quantities, and the corresponding units. So if you use this mass from the ISQ library, you automatically get the associated units with it. So when we say the mass of this vehicle is a kind of mass from this library, then we get the units. And it's a very powerful concept because all of the quantities and all of the standard units are available in this library. You also see an example of the expression language, even though this is a very simple expression. You see that the mass equals the dry mass plus the cargo mass plus the fuel mass. And you see, indeed, the dry mass, cargo mass, and fuel mass are also kinds of mass from the ISQ library. Similarly, you see position, velocity, acceleration are kinds of quantities from the library, as is electrical power. It's a kind of ISQ power. You see one additional quantity here called average fuel economy. Well, the units and the quantities and units for average fuel economy are not contained in the standard library. However, you can create a standard quantity and unit by using the primitives. So you can see that we've named this distance per volume, similar to miles per gallon. And basically, you just set up an expression that this is based on distance and volume, which are in the library. So you can combine and do simple arithmetic on the quantities to derive new quantities. And that's very, very powerful. It's just an example how SysML v2 includes a very powerful library, and there are many others that you can leverage when you're doing your modeling. You also see that it has these 3 ports. Fuel command port is analogous to your acceleration command when, for example, a person puts their foot on the accelerator. An ignition command port, the ignition switch. Vehicle to road port, this is where, in effect, the rubber meets the road, where the tires actually interface to the road. So these are 3 ports. The vehicle has, in this example, only a single action called provide power. And it has a set of states called vehicle states. I'm going to call your attention to the vehicle states because we're going to come back to that and look at the graphical and textual rendering for vehicle states in just a moment. So on the next slide, we're going to see the corresponding textual representation for this part def called vehicle. So here is the textual syntax for the part def vehicle. And you can see it has the attributes that were identified previously. You can see the mass and the dry mass, etc. You can see it has the 3 ports, the action, and the states. So this basically shows the textual syntax reflects the same model as the graphical syntax that you saw a moment before. I'll call your attention to the vehicle states that I referred to on the previous slide. And you'll notice in the textual notation you have these curly brackets. This indicates that there's additional content to the vehicle states. So what we'll look at on the next slide is the graphical representation of the vehicle states. And then the following slide, we will look at the corresponding textual syntax for the vehicle state. So you can see how the model expands and becomes elaborated, if you will. Also want to draw your attention to this attribute electrical power, because you'll see this on the next slide as well. So here are the vehicle states in using the graphical syntax. You can see the name vehicle states here. It's the same as the name in the textual syntax on the previous slide. The keyword parallel indicates that the child states are concurrent states. So you're going to be in an operating state and a health state at the same time. Then you see these actions that are performed in the on state. So upon entry, you perform self-test. Then you do the provide power action. And upon exit, you apply the parking brake. All of these actions can be defined in action flows separately in a separate view and further elaborated. You also see the transition from the off state to the on state. You see there's an ignition command, and it transitions from off to on when that ignition command equals on. Similarly, you'll transition from the on state to the off state when that ignition command equals off. Finally, you see there's a constraint that is imposed during the on state, that the electrical power, that's the attribute I showed on the previous slide, must be less than or equal to 500 watts. Because electrical power was defined based on the library quantity kind of power, I could automatically apply watts and a value with watts, units watts to this attribute. It automatically knows that based on the library. On the next slide, we'll see the textual notation for the vehicle states. So here is the textual syntax that corresponds to the graphical view that we were just looking at. You can see the exhibit state, vehicle states parallel with the first curly bracket. That's what we saw in the vehicle part definition. And then you see the expansion here. It's not all shown. It extends beyond the bottom of the page. But you can see the operating states with the off state and the on state, the entry action, the do action, the exit action. You also see the constraint that the electrical power is less than or equal to 500 watts. You see the transitions from off to on. For example, you're first in the off state, and if the ignition command equals on, you transition to the on state, etc. So that just gives you, again, a sense that the graphical notation and the textual syntax are just two different renderings of the same underlying model, such that if you update one, you would update the other. So let's look at this vehicle part def again. For this approach, this modeling approach, I'm treating the vehicle part def as a black box specification that specifies the key characteristics of a vehicle. Now, this enables me to use this black box specification and come up with different usages of this vehicle that corresponds to different designs with the same vehicle black box characteristics. So in this example, I have vehicle 1. It's called a part as opposed to a part def. So a part is defined by a part def or a part definition. So vehicle 1 is defined by vehicle. What that means is vehicle 1 will inherit all of the features of vehicle, but it can then override them and add to them. So in effect, vehicle 1 can be a design of the vehicle that conforms to the vehicle black box specification over here. So I could have a vehicle 2 that's actually a different design that also conforms to this vehicle black box specification, and I could perform trade-offs on vehicle 1 versus vehicle 2, etc. So in this particular example, we see again, vehicle 1 is a specialization of vehicle, and the inherited features are shown with this little caret symbol, this little circumflex. So these are all the inherited features you can see from vehicle. Some of those features have been what are called redefined. They override the original feature. So for example, dry mass is a kind of mass in the part def vehicle, but it's equal to the sum of the part masses in vehicle 1. So we've overridden the original dry mass with this, if you will, more specialized dry mass. We can also add parts to this design. So down here you see we've added engine and transmission parts to vehicle 1, whereas the vehicle black box did not include any parts. So what you see here on the left is a usage called vehicle 1 of the part def vehicle that inherited its features, overrode some of those features to make them more specialized, and added additional features. In so doing, it allows you to adapt each usage to the context of its use through this process of inheriting, redefining, and adding features. This is the corresponding textual syntax for vehicle 1. It shows vehicle 1 colon vehicle. This is the same as the defined by relationship that I showed previously. And in fact, this can be used in the graphical syntax as well. So vehicle 1 colon vehicle says vehicle 1 is defined by the part def vehicle. Note that the inherited features are not shown in the textual syntax. Only the features that are either redefined or added are shown. So some of those features of the vehicle are not shown, but you can see that dry mass redefines the original dry mass and is now equal to the sum of the part masses. The part masses is a new feature, and you can see it's equal to the engine's mass and the transmission's mass. And you can see the engine here and the transmission, and they are further elaborated with their attributes, their ports, actions, and the engine you can see is composed of 6 cylinders. So you can see a fair amount of elaboration of this vehicle 1 in the textual syntax. The other thing, in addition to seeing the parts elaborated, you see this connect statement, and here you see that the engine drive power port is connected to the transmission's drive power port. In the previous vehicle 1 example, you saw that the vehicle 1 included an engine and transmission, and that the engine included 6 cylinders. Well, this is a simple view showing that decomposition. And of course, as the design gets more complex, this expands out, and so you would see a full parts tree for vehicle 1 at multiple layers. Often, as this graphics gets more complex, you may only show one decomposition level at a time. So for example, I'd show the vehicle with its parts, and then on a separate diagram, I'd show the engine with its parts, the transmission with its parts, etc. We also can show the interconnection view between, in this case, the engine and the transmission. They're part of the vehicle, as we've already seen, and they're connected. Here's the drive power port on the engine that we referred to, and here's the drive power port on the transmission. And there are some other ports that I won't elaborate here in this example. And I'd also like to just say a few more words about a requirement in SysML v2. In SysML v1, We did have a requirement with a text statement, a shall statement. It had an ID. In SysML v2, we've clearly retained that, so we have the ability to provide an identifier. This is a mass requirement. It's a requirements definition. So you'll see that we could have usages of this requirements definition, and we can adapt it, each usage, to its particular context. But this mass requirement then includes a text statement, a shall statement. It includes, importantly, a constraint expression that I referred to earlier. So here we see a simple expression that just says that the mass actual is less than or equal to the mass required. So the important thing about this expression is that it can be evaluated. So you can have a solver that can take the value of mass required, it can take the value of mass actual that comes from, for example, an analysis. It can compare them and evaluate the expression to be true or false. If it's true, the requirement passes. If it's false, it doesn't. So that's really important. A requirement can also include assumed constraints. So you may have an assumption that, for example, this mass only holds for a full tank of gas, for example. So you can specify that assumed constraint as well. And the requirement also shows the attributes that are used in the constraint expression. So here's mass actual and mass required, and you can see that they are also kinds of mass from the ISQ library that we referred to previously. So the ability to specify a requirement more formally like this, beyond just its textual shall statement, enables you to basically verify a requirement through analysis or through test. You can take the actual results of an analysis or test and compare it to the required value and determine whether that requirement passes or fails. And these constraint expressions can become arbitrarily complex, so they're not limited to being just simple expressions like this one here. So now let's pull some of these model fragments that I've been talking to. Let's pull them together to show a simple vehicle model. So in the upper left here, you see a requirement called vehicle specification. So this would correspond to your entire specification on the vehicle. And I'm just showing one requirement, just the mass requirement. And this is a usage of the mass requirement that we were just looking at. Now, in reality, there would be many requirements, and in fact, this would be a tree of requirements. But for simplicity, I'm just showing a single requirement here. And that requirement is allocated to the vehicle 1 that we referred to, the part vehicle 1, and specifically to the dry mass. So you can see this allocate relationship between the requirement and the dry mass on vehicle 1. And just to show some other views of this example, we've already talked about the state-based behavior. So we had the vehicle states, and that in effect is elaborated by this vehicle states graphical representation here showing the state-based behavior. So although it's just designated as a single text string here, vehicle states, it's actually fully elaborated in the model. And the model I mentioned has a do behavior called provide power. And in this case, although I didn't show it previously, here's the provide power. This is an action flow view of provide power showing the engine generating torque and the transmission amplifying torque. Obviously, there would be other parts of the vehicle that would be performing other actions. And you saw the decomposition view of the vehicle into its parts. Again, here's the engine, transmission, and the 6 cylinders. And the interconnection view showing the engine connected to the transmission. And a verification case showing this mass test is being used to verify the mass requirement. And there's some specific information in terms of the objectives of the test, the verification method, the actions that are taken by this method to weigh the vehicle and to evaluate pass-fail, and other information in that mass test. So these are just some samples of how a model is developed and built and provides you a broad view of your system under development as a system model. And of course, there are many other views that we didn't touch on. So now I'm going to talk about connecting SysML v2 to other models and tools and applications using this application programming interface, this standardized API that SysML v2 provides. So what you see in the center is representative of the repository of data that stores the system modeling information, the structure, the behavior, the requirements, etc. And you see wrapped around it is this API. And this API wrapper enables other applications and tools to access the information in the repository and update it or query it or navigate it or do other things to this data. So let's look at a few examples. So here's an example of a CAD viewer application. It's actually FreeCAD, open source CAD viewer, and it's showing a graphical rendering of geometry of a simple drone with a sensor and its field of view indicated here. And this information on the geometry actually came from the SysML v2 model and extracted from the model and rendered in the CAD viewer. So this is an example where we have captured certain information in the SysML v2 model, maybe early in the design process, and then rendered it using this CAD viewer. And as the model evolves in fidelity, then that CAD model may take precedence over the SysML v2 model, but we can continue to provide connections between the elements in the SysML v2 model and the elements in the CAD model. This is another example, an application called Maple, which is a sophisticated analytic solver that extracted equations from the SysML v2 model that were in an analysis case, extracted those equations, solved them, and generated its own visualization of the analysis results. So again, this used the API to access the SysML v2 model and extract those equations. This is a third example of a graph visualization application called Tom Sawyer that extracts information from the model and then renders that information in a graph. And this is an example where we anticipate SysML v2 vendors will be able to provide very sophisticated and engaging graph visualizations, such as 3D graph visualizations, perhaps dynamic 3D graph visualizations, which we'd really like to see. And the final example here is an application called Sandia, which basically extracts model information and then applies some of the API configuration management services to manage that data. It basically defines commits where it specifies those elements that changed from one commit to another. And in so doing, it's able to synchronize this data with other models and applications and their versions. So it maintains and manages that overall digital thread that I was referring to. So each of these orange circles actually corresponds to different commits. And it also provides for branch and merge capability and the like. So it's a very, so the API provides a very powerful capability to have a standard way that enables interoperability with a broad range of applications and tools.